We tend to see the universe through a mirror. We look up from our small blue world orbiting a stable shining yellow star, and we instinctively assume that what we have is normal. It is a deeply human way of thinking. We are the default, the standard, the template for what life looks like. For decades, this assumption, often unspoken, has guided our search for life elsewhere in the cosmos. We have been looking for worlds like our own orbiting stars, just like our Sun. But astronomers are by nature practical. While searching for a second Earth is a noble and inspiring goal, the sheer statistics of our galaxy suggested a different, more logical place to look. Our Sun. A G-type star is actually quite rare in the grand scheme of things. The vast, overwhelming majority of stars in our Milky Way galaxy are not like our Sun at all. They are M-dwarfs, more commonly known as red dwarfs. These small, dim, reddish stars are the undisputed rulers of the galaxy. They make up a staggering 75% of all stars. Not only are they everywhere, but they are also incredibly long-lived. While our Sun will burn through its fuel and die in another 5 billion years or so, a red dwarf can patiently sip its nuclear fuel for trillions of years, a time frame far longer than the current age of the universe. On paper, they seemed like the perfect hunting ground. If you have more lottery tickets, you have a better chance of winning. Red dwarfs, with their sheer numbers and immense lifespans, offered the universe an almost infinite number of chances and an almost infinite amount of time to spark life. The habitable zones, the Goldilocks region where liquid water could exist on a planet's surface, might be much closer to these cooler stars, but they were there. For decades, the astrobiology community focused its greatest hopes on these dim red suns. They were, it seemed, the galaxy's best bet. Then a new troubling idea began to emerge, one that has shaken the foundations of this search. A growing body of research, culminating in a profound statistical puzzle, has suggested this assumption isn't just slightly off. It might be, in the words of some researchers, completely wrong. What if these trillions upon trillions of red dwarf stars, the most common homes in the cosmos, are not nurturing cradles for life? What if they are instead cosmic dead ends for anything complex? This shocking pivot in thinking stems from a simple yet profound observation about our own existence. This is the story of the red sky paradox. The puzzle was brought into sharp focus by astrophysicist David Kipping. He looked at the same data as everyone else, the fact that red dwarfs make up 3/4 of all stars, and asked a question so simple it was almost heretical. If red dwarfs are the default, and if they are just as good or better at producing life as stars like our Sun, why aren't we living under a red sky? This is the core of the paradox. We are a data point. We are so far the only example of complex intelligent life we know of. And we exist around a G-type star, our Sun, which belongs to a class that makes up only about 7% of stars. We are not orbiting the most common type of star. We are orbiting a relative rarity. Why? Why would life, and specifically complex life like us, arise around a statistical outlier? This is not a small discrepancy. If you were to reach into a bag that contained 75 red balls and 7 yellow balls, and you pulled out a yellow ball on your very first try, you would have to pause and wonder. You would have to ask yourself, is there something special about this yellow ball, or am I just incredibly lucky? This is precisely the question Kipping set out to answer, and he used a powerful tool to do it: Bayesian statistics. This branch of statistics is not just about counting things, it's about updating our beliefs based on new evidence. It is the perfect tool for comparing two competing ideas or hypotheses to see which one is more likely to be true given the one piece of evidence we have. In this case, the evidence we have is our own existence. We are Team Sun. We know for a fact that complex life can arise around a sun-like star. The question is how to interpret this single data point. Kipping set up two main hypotheses to battle against each other. The first hypothesis is that there is nothing special about our Sun. It says that red dwarfs, M dwarfs, are just as capable of producing complex life as sun-like stars, G dwarfs. The reason we find ourselves orbiting a G-dwarf is simply a matter of cosmic chance. We just happen to be one of the lucky few. It's like winning a lottery with very poor odds. Someone has to win, and it just happened to be us. In this view, our existence tells us nothing meaningful about the universe. We are just an anomaly, a statistical fluke. The second hypothesis is far more dramatic. It states that there is a reason we are here. It argues that red dwarfs are, for some fundamental reason, terrible places for complex life to evolve. Perhaps they are too violent in their youth, blasting their planets with deadly flares. Perhaps their planets are tidally locked, with one side perpetually burning in the star's gaze and the other perpetually frozen in darkness. Perhaps the close inhabitable zones mean planets are stripped of their atmospheres. Whatever the specific reason, this hypothesis suggests that the deck is stacked against red dwarfs. In this scenario, our Sun-like star isn't a statistical outlier, it's a prerequisite. Life, especially complex life, prefers stars like our Sun. We didn't win a lottery with bad odds. We simply showed up at the only game in town that could actually produce a winner. Kipping ran the numbers. He used the Bayesian framework to weigh the likelihood of our own existence under both scenarios. How probable is it that we would find ourselves around a G-dwarf if the lucky hypothesis were true? And how probable is it if the red dwarfs are bad hypothesis were true? The result was stark. The evidence, he concluded, strongly favours the second hypothesis. The odds that we are just a fluke or lucky accident around a rare star type when the much more common red dwarfs were just as good are very low. The statistical analysis showed that the red dwarfs are bad hypothesis is many, many times more likely to be the correct explanation for our existence. To put it simply, the universe had a choice. It could have put us around one of the trillions of red dwarfs. It did not. It put us here. Statistically, the most logical and least surprising explanation for this fact is that the choice was not a real choice at all. Something is fundamentally wrong with red dwarfs. The fact that we are here under a yellow sun is not a paradox, it is a clue. It is a powerful piece of evidence screaming at us from across the galaxy that the most common stars in the sky are not where we should be looking for our counterparts. They may be cosmic dead ends, leaving stars like our Sun as the true rare cradles of complex life. When we look for life in the galaxy, our eyes are naturally drawn to red dwarf stars. It makes sense. They are the most common type of star, making up maybe 75% of all the stars in our Milky Way. They are the silent majority. On the surface, they seem perfect. They're incredibly long-lived. Our Sun will burn out in another 5 billion years, but a red dwarf will sip its fuel for trillions of years. They offer stability over time, a seemingly endless gentle glow. If you were looking to place a long-term bet on life, these stars seem like the safest bet in the casino. But this is a tragic illusion. The reality of a red dwarf system is not calm and stable. It is a place of profound and unrelenting violence. The very things that make a red dwarf what it is also make its planetary system some of the most hostile places imaginable for life as we know it. The first and most immediate danger is the star's temper. Red dwarf stars are famous for throwing tantrums in the form of superflares. When we think of a solar flare from our own Sun, we think of beautiful auroras, the northern lights. On rare occasions, a strong flare might disrupt our radio communications or satellites. It's a minor inconvenience. A red dwarf superflare is not a minor inconvenience, it is a cataclysm. These are magnetic explosions that are hundreds or even thousands of times more powerful than the flares our Sun produces. And they are not rare. Our Sun might have a big flare every few years. A young active red dwarf can unleash multiple planet-sterilizing superflares every single day. Imagine the most powerful solar storm in human history, the kind that could wipe out our electrical grid, hitting Earth 3 or 4 times between breakfast and dinner. This is the normal weather forecast for a red dwarf system. These flares are not just flashes of light, they are focused blasts of high-energy radiation. They are shotgun blasts of X-rays and deadly ultraviolet light washing over any nearby planets in a flood of sterilization. This radiation is strong enough to shred complex molecules, the building blocks of life. This brings us to the second problem, which is tied directly to the first. Because a red dwarf star is so dim and cool, its habitable zone is incredibly close to it. The habitable zone, sometimes called the Goldilocks zone, is that perfect narrow band where the temperature is just right for liquid water to exist on a planet's surface. Not too hot that it boils, not too cold that it freezes. For our bright hot Sun, this zone is comfortably far out-centered on Earth's orbit. We are at a safe distance from the Sun's own temper. But for a dim, cool red dwarf, a planet has to huddle close to the star just to stay warm. The habitable zone for many red dwarfs is closer to the star than Mercury is to our Sun. The planets are practically skimming the star's surface. Now you see the horrifying connection. The planets that are in the only place where liquid water could exist are also in the direct line of fire. They are sitting in the front row, directly in the kill zone for those daily superflares. They have no protection, no distance to weaken the blow. Every single day, these worlds are scoured by X-rays and ultraviolet radiation that is thousands of times stronger than what Earth receives. The consequences of this are predictable and devastating atmospheric stripping. A planet's atmosphere is its shield. It's a bubble of gas that protects the surface, provides air to breathe, and creates the pressure needed for liquid water to exist. But that shield is not indestructible. When this constant brutal barrage of high-energy radiation from the superflares slams into the top of a planet's atmosphere, it physically sputters and it blowing it away molecule by molecule. It's like a cosmic sandblaster. The high-energy X-rays and ultraviolet light give the atoms and molecules in the upper atmosphere like nitrogen, oxygen, and even water vapor a powerful kick of energy. This kick is so strong that it accelerates them past the planet's escape velocity, and that they are lost forever, flying off into deep space. This process may be slow, but it is relentless. Over millions of years, the atmosphere is simply stripped away, eroded down to nothing. And as the atmosphere thins, the air pressure drops. Without sufficient air pressure, liquid water is impossible. It doesn't matter what the temperature is. If you were to pour a cup of water on the surface of a planet with no atmosphere, it wouldn't make a puddle. It would instantly boil away violently into space. So a planet that starts as a beautiful blue water world, a potential second Earth, will be tortured. Its oceans will boil, its atmosphere will be stripped, and it will be reduced to a dry, airless, radiation-baked rock. This isn't a possibility, it's an inevitability. Even if a planet could magically hold on to its atmosphere, it faces another stranger danger: tidal locking. When a planet orbits a star very closely, the star's immense gravity pulls on it unevenly. This tidal force acts like a brake, slowing the planet's rotation down over time until it stops spinning relative to the star. The end result is the same as our Moon and Earth. We only ever see one side of the Moon. A planet in the habitable zone of a red dwarf will almost certainly become tidally locked. This means one side of the planet is locked in permanent eternal daylight and the other side is locked in permanent eternal night. Let's imagine what this world would be like. The day side faces the red dwarf forever. Even though the star is dim, it is so close that it dominates the sky, hanging in the same spot, unmoving for all time. The surface on this side is baked relentlessly. Any water would have boiled off billions of years ago. It is a scorched, endless desert where the temperature might be hot enough to melt lead. Now let's fly over to the night side. This side never ever sees the sun. It faces the cold black emptiness of space. Here the temperature plummets to hundreds of degrees below zero. Any atmosphere that dares to drift over here will freeze solid and fall as snow. This isn't water snow. It's a permanent growing ice cap of solid nitrogen and frozen carbon dioxide. It is a land of ultimate cold and darkness. This creates an extreme, bizarre climate. The only place life could possibly exist is in the Terminator Zone, a thin, permanent ring of twilight that separates the scorching day from the frozen night. Here in this land of eternal sunset, the temperature might be just right, but it would not be a peaceful place, though. The incredible temperature difference between the hot side and the cold side would create the most violent weather in the galaxy. The atmosphere, if any is left, would be in a constant state of panic trying to balance the heat. This would create winds that would make our worst hurricanes look like a gentle breeze. We are talking about supersonic winds, a permanent global storm raging from the day side to the night side. Imagine trying to build a shelter or for life to even begin in a world-spanning non-stop wind tunnel that is screaming past at faster than the speed of sound. As if all of this wasn't enough, we come to the final fatal blow, the nail in the coffin. We have been discussing these stars as they are now, but stars like people have a childhood, and the childhood of a red dwarf is not just active, it is a period of pure unadulterated rage. For the first billion years of its life, a red dwarf is wildly unstable. It spins much faster, its magnetic fields are a chaotic mess, and it is in a state of superactivity. All the problems we just listed, the flares, the radiation are not just worse during this period, they are on a completely different scale. The superflares are likely 10,000 times stronger. The X-ray and ultraviolet radiation is so intense it's hard to even comprehend. And this isn't a short phase. This period of extreme violence lasts for 1 billion years. Let's put that in context. On Earth, life began within the first billion years. That's when the first simple cells, the first delicate chemistry got started in our oceans. That was our planet's nursery phase. For a planet around a red dwarf, that first billion years is not a nursery. It is a sterilization chamber. Any planet in the habitable zone is being boiled, blasted and scoured. There is no chance for a primordial soup. Any attempt by complex molecules to form is immediately shattered by a blast of radiation. Any water is boiled away. Any atmosphere is stripped before it can even form. By the time the red dwarf finally calms down after a billion years of fury and settles into its long, stable adulthood, it's too late. The planets in its habitable zone are already dead. They are burned out, airless, tidally locked and sterilized husks. This is the great terrible tragedy of the red dwarf stars. They are the most common homes, the most abundant real estate in the galaxy. They tempt us with the promise of trillions of years of stability. But it is a false promise. They are a trap. The very habitable zone they offer is in reality a torture chamber, a place where the dream of life is killed before it can even begin. In our grand search for life in the cosmos, it feels like we are finally in a golden age. Our telescopes and technologies have become so powerful that we are no longer just hoping to find planets, we are finding them by the thousands. Every week it seems a new announcement hits the news, another super Earth, another habitable zone candidate, another strange new world. This flood of data has given us a new picture of the galaxy, one teeming with planets. But there is a dangerous trap hidden in this data. This trap is called observational bias, or selection bias. It's one of the most common and powerful ways that scientists and all of us get fooled. Think of it this way. Imagine you lose your keys in a park in the middle of the night. Where do you look for them? You look under the one single streetlight that is working. You search and search in that small circle of light. After 10 minutes you find a $5 bill. A minute later you find a glove, then you find a handful of coins. You might start to think, wow, this spot in the park is where everyone drops their stuff. This must be the most common place for lost items. The truth, of course, is that you have no idea. You didn't find those items because that spot is special. You found them because that is the only place you could see. Your keys are probably still lost in the dark grass 50 feet away. This is the streetlight effect, and it is exactly what is happening in our search for planets. We are only looking where the light is. A critical voice might interrupt here and say, but what about TRAPPIST-1? That system is incredible. We found 7 Earth-sized planets, many in the habitable zone, all orbiting one star. This proves that systems like this are common and are great places to look for life. This is a perfect point. The discovery of the TRAPPIST-1 system was a landmark moment for astronomy. It's exciting, it's dramatic, and it's exactly the kind of target that gets scientists and the public dreaming of other worlds. But here is the hard truth. The discovery of TRAPPIST-1 doesn't prove that these systems are the best. It proves that they are the easiest to find. The excitement over TRAPPIST-1 is a perfect demonstration of our observational bias. We are celebrating finding coins under the streetlight. The reason for this is simple. That is a selection bias. Our methods for finding planets are heavily skewed in a way that makes systems like TRAPPIST-1 jump out at us while making systems like our own solar system almost invisible. Let's break down why. Our most successful method for finding exoplanets is called the transit method. This is what the famous Kepler and TESS space telescopes use. The idea is simple. You stare at a star and wait for a planet to pass in front of it. When the planet transits the star, it blocks a tiny fraction of the star's light, causing a very slight dip in its brightness. If we see this dip happen at a regular repeating interval, we know we've found a planet. This is where the bias comes in. The star in the TRAPPIST-1 system is a tiny, cool red dwarf star. It's not a big, bright star like our Sun. It's barely larger than the planet Jupiter. Now imagine you are using the transit method to look at a star like our Sun. To find a planet like Earth, you are trying to see the shadow of a gnat as it flies in front of a giant blazing stadium floodlight. The dip in brightness is almost zero. It is incredibly difficult to measure close to the limits of our technology. But now imagine you are looking at a red dwarf star like TRAPPIST-1. You are still looking for an Earth-sized planet, the gnat, but this time the star is a tiny dim flashlight. When the gnat flies in front of the small flashlight, it blocks a huge percentage of the light. The dip in brightness isn't tiny anymore, it's massive, it's obvious, it's unmistakable. So what happens? Our telescopes, which are programmed to find these dips, are naturally finding thousands of planets around red dwarf stars. It's not because there are necessarily more habitable planets there, it's because any planet that is there is screaming at us while the planets around sun-like stars are whispering so quietly we can't hear them. This bias is compounded by a second method, the radial velocity or wobble method. This method watches the star itself. A planet's gravity doesn't just pull on other planets, it also pulls on its star, making the star wobble back and forth. A low-mass star like a red dwarf is a lightweight. An Earth-sized planet pulling on it can create a very noticeable wobble that we can detect. But a massive star like our Sun is a heavyweight. An Earth-sized planet pulling on it creates a wobble so tiny that it is once again almost impossible to see. This is the conclusion we must face. We find them a lot, not because they are better, but because they are easier to see. This convenience in observation is fooling us. It's a technological illusion. It has led us to focus our attention, our resources, and our hopes on these red dwarf systems. We are writing headlines about them, and we are building our scientific models based on them all, because they were the low-hanging fruit. We have mistaken what is visible for what is true, and this more than any other reason is why we are being dangerously misled in our search for a second Earth. So we have a problem. The most common stars in the galaxy, the red dwarfs, seem overwhelmingly hostile to life as we know it. Their habitable zones are a chaotic environment of radiation and gravitational traps. If the vast majority of planets in the cosmos are orbiting these violent dim stars, then where is all the life? This leads us to a more selective and perhaps more sobering possibility. What if we have been looking in all the wrong places? What if the type of star matters more than anything else? We have been so focused on finding Goldilocks planets that we forgot to search for Goldilocks stars. When we look for this perfect star, a true cradle for life researchers like David Kipping have identified a very specific sweet spot. This ideal range is not about brightness or temperature, but about mass. The perfect star, according to this model, must have a mass between roughly 0.74 and 1.6 times the mass of our own Sun. What does this mean in practice? It means the ideal hosts for life are stars very much like our own. This mass range almost perfectly describes G-type stars, the yellow dwarfs, like our Sun, and K-type stars, which are slightly smaller and more orange. These stars, it turns out, are special. They are the Goldilocks stars, and they are perfect for three very specific reasons. First, and perhaps most importantly, is stability. Unlike the volatile red dwarfs that spend their first billion years lashing their inner planets with deadly flares, G-type and K-type stars are incredibly stable. They are the calm, predictable hearths of the cosmos. They settle down quickly after they are born and then enter a long, stable main sequence, burning their hydrogen fuel at a steady, consistent rate for billions of years. They produce far fewer superflares and bathe their planetary systems in a reliable stream of light and warmth. Life, especially complex life, does not just need energy, it needs predictable energy. Evolution is a slow, methodical process that requires a stable environment. It cannot get a foothold if the entire planet is being sterilized by radiation every few million years. A G-type star provides a calm harbor, a safe space where the delicate, complex chemistry of life can slowly build upon itself over geological time without being constantly reset to zero by a stellar tantrum. The second reason is time. The universe is full of massive, brilliant stars, O-type and B-type stars that blaze blue-white and are thousands of times brighter than our Sun. But these stars are the live, fast-die young rock stars of the galaxy. They burn through their fuel in a cosmic instant lasting only a few million, or perhaps tens of millions of years. This is not remotely enough time for life. On Earth, it took nearly 4 billion years to go from the first single-celled organism to a creature that could walk on land. It took hundreds of millions of years more to evolve consciousness. Complex life is not a sprint, it is an endurance marathon. G-type and K-type stars are the ultimate marathon runners. Our Sun, a G-type, has a total lifespan of about 10 billion years. It has already provided a stable home for Earth for 4.5 billion years, and it will continue to do so for several billion more. This multi-billion year window is the minimum time required for the slow, grinding, patient process of evolution to experiment, to fail to adapt, and to eventually build complexity. Stars more massive burn out too fast, stars less massive. The red dwarfs last for trillions of years, but as we've seen, their other conditions are too hostile. The 10 billion year lifespan of a Sun-like star appears to be the perfect cosmic timer for the evolution of something interesting. The third reason is space, the habitable zone. Because G-type and K-type stars are so much brighter and hotter than red dwarfs, their habitable zone, the region where liquid water can exist, is pushed much, much farther out. Our Earth orbits the Sun at a comfortable distance of 93 million miles. At this safe distance, we are completely free from the dangers of tidal locking. Our planet is free to rotate, creating the gentle cycle of day and night that distributes the Sun's energy evenly across the globe. This rotation drives our weather, our ocean currents, and our planet's stable magnetic field. A planet in the habitable zone of a red dwarf must huddle dangerously close to its star just to stay warm. At that proximity, the star's gravity would almost certainly lock the planet's rotation, leaving one side in a perpetual scorching day and the other in an eternal frozen night. Furthermore, being that close means the planet is unprotected from the star's stellar wind, which can strip away an atmosphere in a geological blink. A Sun-like star's habitable zone is a safe, protected region. A planet orbiting there can spin, it can form a robust magnetic shield, and it can hold on to its precious atmosphere and oceans for billions of years. So we have our perfect host, a stable, long-lived star with a safe, distant, habitable zone. This brings us to the most critical point of all. These stars are rare. G-type and K-type stars, the Goldilocks stars, make up only about 10% of all stars in the Milky Way. The other 90% are mostly the violent red dwarfs or the short-lived blue giants. This single fact changes everything. It leads to a profound hypothesis, something we might call solar hegemony. The word hegemony means dominance or leadership. This theory suggests that sun-like stars are not just one possibility for life. They may be the only possibility for complex multicellular or intelligent life. It suggests that we are not lucky. We are simply the product of a cosmic minority. It implies that the universe is not teeming with alien civilizations around every corner. Instead, it suggests that the vast majority of the cosmos is hostile. This paints a stark, chiming and somewhat lonely picture. It suggests the universe may be filled with literally trillions of silent planets. Trillions of worlds orbiting dim red suns bathed in a permanent dark red sky. Worlds that are either idly locked wastelands or irradiated rocks scoured clean of any chance for complexity. The universe may be full of these failed worlds, silent, sterile and lifeless, trapped in orbit around the wrong kind of star. The galaxy in this view is a vast, dark and quiet ocean, and scattered very, very far apart in this ocean are a few tiny, precious islands of light. These are the systems orbiting G-type and K-type stars. These are the only places where the conditions are right. These are the true cradles of life, and we are living on one of them. This entire line of reasoning, this conclusion that red dwarf stars are a false hope, would be meaningless without proof. Science is not built on compelling ideas, it is built on hard, verifiable data. So when we make the claim that these billions of worlds are hostile, we must answer the most important question: how do we know this? The evidence has been gathered by a generation of our most powerful telescopes, each looking at the universe in a different kind of light. We began by using instruments like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS. Their primary job was to find the planets. They did this by staring at stars and waiting for the tiny rhythmic dip in brightness that happens when a planet passes or transits in front of its star. But in doing this, they also recorded everything else the star was doing. They gave us a perfect minute-by-minute log of the star's behaviour, and what they saw was alarming. These red dwarf stars were not stable. Their light levels were constantly violently flickering. They were experiencing super flares, sudden catastrophic explosions of energy. But Kepler and TESS mostly see invisible light, the same light our eyes see. The real danger from a flare is not the visible light, it's the invisible high-energy radiation. To see that we needed different eyes, we turned the Hubble Space Telescope to look at these stars in ultraviolet light. Hubble saw that these flares were blindingly bright in the very wavelengths that are most damaging to life's molecules like DNA. Then we used the Chandra X-ray Observatory. Chandra sees the highest energy radiation, the X-rays, which are powerful enough to physically knock molecules out of an atmosphere and send them flying into space. Chandra's observations confirmed our fears. These habitable systems were being flooded with X-rays at levels hundreds or even thousands of times more intense than what our own sun produces. The discovery was this: the habitable zone of a red dwarf is not a peaceful sanctuary, it is the star's kill zone. The data from these observatories working together painted a clear picture of intense, violent stellar activity happening right where we hope to find life. Let's look at a specific case. This isn't just theory, it's a recorded event. Our closest stellar neighbour is a red dwarf called Proxima Centauri. It has a planet, Proxima Centauri b, orbiting squarely in its habitable zone. It is the closest possible place for life outside our solar system. In 2016, astronomers were watching this star. Suddenly it erupted in a superflare. In a matter of minutes, the star became 14,000 times brighter in ultraviolet light than normal. Think about what that means. A sudden planetary scale blast of radiation equivalent to thousands of our own sun's worst flares all at once. Any budding life on the surface of that world would have been sterilized, its core genetic code shredded. The top layer of any ocean would have been boiled. This event was not a small sunburn, it was a cosmic sterilization. And this was not a one-time event. We see this star and others like it flaring regularly. Proxima Centauri b is being hit with this level of radiation not just once, but over and over again. Seeing these flares led to the next logical step: modelling. Scientists at universities like the University of Chicago and institutes like the Max Planck Institute took this real-world data and plugged it into complex computer simulations. The question was simple. If you take an Earth-like planet with an Earth-like atmosphere and put it next to a star like Proxima Centauri, what happens? The results were devastating. The models showed that these repeated flares blasting the planet with X-rays and extreme ultraviolet light would physically strip away the atmosphere. The high-energy particles would hit the gas molecules in the upper atmosphere like tiny cannonballs, giving them enough energy to escape the planet's gravity forever. The models showed that this process called atmospheric escape is incredibly fast. An atmosphere that took billions of years to form on Earth would be completely showered away in less than 100 million years. 100 million years is nothing. On Earth, it took more than 3 billion years for complex multicellular life to evolve. These models show that on a red dwarf planet, the atmosphere is gone before life even has a chance to get started. The planet is left as a naked, airless rock. But this leads to a common counter-argument. What about a magnetic field? Earth is protected from our sun's solar wind by a strong magnetic shield generated by our planet's rotation and its molten iron core. Surely a planet around a red dwarf could have one too. This is where the problem gets worse. Because the planet is so close to its star, to stay warm it becomes tidally locked. Just as our moon always shows the same face to Earth, this planet will always show the same face to its star. One side is locked in permanent, scorching daylight. The other is locked in permanent frozen night. This tidal locking has a fatal consequence. It dramatically slows the planet's rotation. Instead of spinning once every 24 hours, it might spin only once every 50 or 100 days. This slow rotation is thought to be catastrophic for the magnetic field. A planet's magnetic shield, its dynamo, is believed to require a fast spin. If the planet's rotation slows to a crawl, the dynamo sputters and dies. The magnetic field weakens or perhaps never even forms at all. So at the exact moment the planet needs its shield, the most to defend against the star's superflares, that shield is disabled by tidal locking. It is a terrible catch-22. The very location that gives the planet a chance at liquid water is also the location that guarantees it will be defenseless. There is a second counter-argument. What if the planet starts with a lot of water? A water world with deep oceans. Couldn't that survive? Again, the evidence points to no. This is because of what happens during the star's youth. When a red dwarf is very young, it goes through a saturation phase where it spins incredibly fast and erupts with even more violence than it does in its old age. All of that intense radiation, especially the ultraviolet light, does something very specific to water. It triggers a process called photolysis. The high-energy light beams down and hits the water molecules, which are made of 2 hydrogen atoms and 1 oxygen atom, and violently splits them apart. What happens then? The hydrogen, being the lightest element in the universe, simply floats away. It escapes the planet's gravity and is lost to space forever. What is left behind? Oxygen. This sounds good at first, but it is not. This is not the life-giving oxygen we breathe. This is a massive, crushing, toxic atmosphere of pure oxygen. As this highly reactive gas builds up, it poisons the planet. It aggressively oxidizes or rusts the entire surface, turning the world into a red dead desert, much like Mars. Any water that was not split apart is locked away as ice on the permanent night side. So even if a planet starts with water, the star's radiation first boils it, then splits it, then sends the hydrogen into space, leaving behind a toxic, rusty graveyard. For years, this was all our best theory. It was a strong case, but it was indirect. We needed to see it for ourselves. We needed the smoking gun. That evidence arrived in 2024 thanks to the James Webb Space Telescope JWST. Astronomers pointed this revolutionary telescope at the most famous red dwarf system of all, TRAPPIST-1. This system was our greatest hope. It has 7 rocky Earth-sized planets, with at least 3 of them orbiting in the habitable zone. The James Webb Telescope has a unique ability. It can sniff the atmospheres of exoplanets. As the planet passes in front of its star, the star's light filters through the planet's atmosphere. By analysing that light, Webb can see the chemical fingerprints of the gases present. Scientists used Webb to look for the most important sign of habitability water vapour. They found nothing. The observations were a stunning confirmation of our fears. The inner planets of the TRAPPIST-1 system, the ones in the habitable zone, showed no sign of any atmosphere at all. And specifically, there was no trace of water. The models were correct. The theories were right. These worlds are not lush blue-green Edens. They are dry, airless, irradiated rocks. The James Webb Telescope showed us that these planets, our best and brightest hope, are barren. This direct observation is perhaps the most powerful piece of evidence we have. Finally, there is a powerful piece of statistical evidence. This is a form of logic called Bayesian reasoning, which in simple terms means we must use the evidence we do have to update our beliefs about the evidence we don't have. Here is the evidence we have: we exist. Now let's think about the numbers. Red dwarf stars are the most common type of star in our galaxy by far. About 75% of all stars are red dwarfs. Our star, a G-type yellow dwarf, is rare. There are at least 20 red dwarfs for every one star like our Sun. If life can easily arise on planets in the habitable zones of red dwarfs, then life should be everywhere. The galaxy should be teeming with civilizations, and the vast majority of them would have evolved around red dwarf stars simply because there are billions more of them. The statistical probability would be overwhelming, but where are they? We see no evidence of them. And more importantly, we are not one of them. We are here orbiting our rare, calm, stable yellow star. Our own existence is a data point. The fact that we are here and not there is evidence. It strongly implies that here is special. It suggests that the conditions around stars like our Sun are perhaps the only conditions that allow complex life to survive and evolve over the billions of years. The odds of a red dwarf system actually being habitable when all is said and done might be as low as 1 in 10,000 or even worse. Our existence, therefore, is not just a random fluke. It is a piece of evidence. It is the universe telling us that the calm, quiet stability we enjoy is the exception, not the rule. The habitable zones of red dwarfs are a statistical illusion, a trap. The silence we see in the cosmos is the proof. We have explored the haunting silence of the cosmos, the vast distances, and the cosmic catastrophes that seem to filter out life. We have looked at the problem of time and the puzzle of 3-eye Atlas. Yet a fundamental contradiction remains, one that sits at the very heart of our existence. It is the red sky paradox. The paradox is simple. The most common type of star in our Milky Way galaxy is not the yellow, sun-like star we orbit, not by a long shot. The overwhelming majority, perhaps 80% of all stars, are small, dim and red. They are called red dwarfs. These stars are cosmic Methuselahs. While our own Sun will burn out in another 4 or 5 billion years, a red dwarf will burn slowly and steadily for trillions of years. They offer almost limitless time for life to emerge and evolve. If life is a game of chance and numbers' game, then the vast majority of winning tickets should be in red dwarf systems. By all logic, we should find ourselves on a planet bathed in the dim, crimson light of a red star. We should look up at a red sky, but we do not. We look up at a bright blue sky created by the atmosphere of a planet orbiting of a relatively rare, short-lived yellow star. This is the paradox. Why are we the observers in the cosmic minority? The answer is perhaps the most profound concept we have yet discussed. It is called the anthropic principle, or as we will call it here, the universe's self-selection. The principle is this: the universe does not just have to create life, it has to create observers. The fact that we are here asking the question, why are we here, is not a random outcome. It is a fundamental piece of data. It tells us that the conditions in our location must be by definition suitable for the evolution of creatures who can ask that question. We are not just life. We are complex, multicellular, technological, intelligent life. This is a crucial distinction. The leap from a single-celled organism, a simple bacteria, to a creature that can build a radio telescope is the single greatest hurdle in the universe. It requires one resource that is more precious than water, more important than carbon time. Not just a lot of time, but a specific kind of time. It requires billions of years of stable, uninterrupted peace. This is where the red dwarf systems, the supposed galactic majority, fail. They are not the stable havens we imagined. For a planet to be warm enough for liquid water around a dim red star, it must orbit incredibly close. This closeness creates two fatal problems. The first is tidal locking. The planet becomes locked to its star just as our moon is locked to Earth. One side of the planet faces the star forever, becoming a scorched, lifeless desert. The other side faces away, becoming a frozen, dark wasteland. Life might be possible in a thin twilight zone between these two extremes, but it is a harsh, limited, and brutally difficult environment for complex ecosystems to flourish. But the second problem is the true killer. Red dwarfs are violent and angry, especially in their youth. They are flare stars. They erupt with super flares, massive bursts of high-energy X-rays and ultraviolet radiation far more powerful than anything our own sun produces. These flares would be catastrophic for a nearby planet. They would blast the surface with sterilizing radiation. More importantly, over millions of years, they would hit the planet like a sandblaster, stripping away its atmosphere molecule by molecule. Without an atmosphere, there can be no liquid water, no protection, and no chance for life to even begin. So what does this mean for the red sky paradox? It means that red dwarf systems are not failures at creating life. They might be excellent at it. Perhaps their oceans shielded by ice on the dark side and deep underground are teeming with simple single-celled organisms. They might be the greatest bacterial nurseries in the galaxy. But they are terrible at creating observers. Every few million years, a superflare erupts. The radiation pulse boils the surface. Any life that has begun to crawl out of the ocean is immediately exterminated. Any attempt at complexity is beaten back down. The evolutionary reset button is pressed over and over for billions of years. Life on these worlds is stuck at stage 1. It never gets the peace it needs to make the great leap from bacteria to a thinking aware creature. It never gets past the single-cell stage. Now look at our home. Our yellow star, the Sun, is a model of stability. It is calm. It does not erupt in civilization-ending superflares. Our planet is not tidally locked. We have a day-night cycle that stabilizes our climate. We have a strong magnetic field that shields us from the worst of the sun's radiation. This stability is the key. Our solar system provided that one precious resource 4 billion years of relative uninterrupted peace. This long, quiet, boring stretch of time allowed life to experiment. It allowed for photosynthesis, for multicellular life, for fish to crawl onto land, for mammals to rise, and eventually for a species of primate to evolve the brain complex enough to look at the stars and wonder. This solves the paradox. We do not see a red sky because red dwarf systems do not produce observers. The universe self-selects for its audience. If a civilization is capable of asking, why are we orbiting this kind of star? It will always find itself orbiting a stable, calm, boring star like our Sun. It's the only place in the cosmos where the journey from microbe to mind could be completed without interruption. We are not the statistical majority. We are the statistical survivors. The silence from the red dwarf systems is not a mystery. It is the logical outcome of a violent and chaotic universe. The observers can only be born in the quiet, protected, and rare cradles of the cosmos. We are here not in spite of the odds, but because we are the living proof of the one path that worked. When we look for life in the universe, this is not just a philosophical question. It is a practical one. We have limited resources, and our new powerful telescopes can only look at one star at a time. Where should we point them? This question has ignited one of the most intense and important arguments in modern science, the debate over red dwarf stars. For decades, we assumed life would be found around stars like our own, a stable yellow G-type star. But these stars are rare. The vast majority of stars in our galaxy, perhaps 75% or more, are small, dim, cool stars called red dwarfs. They are the neighborhood's dominant population. If these stars can host life, then life might be everywhere. If they cannot, then life may be incredibly heartbreakingly rare. This is the central conflict. Today, this debate is no longer just theoretical. We finally have data. Instruments like the James Webb Space Telescope are giving us our first real answers, and those answers are forcing us to confront a difficult reality. The community is now split into two main camps, and the evidence is tipping the scales in a dramatic and perhaps very lonely direction. The solar hegemony Kipping's camp. On one side of the debate is a group we can call the solar hegemony camp. This view is championed by astronomers like David Kipping, and their conclusion is bleak, simple and powerful red dwarfs are fundamentally hostile to life. Their argument is not based on prejudice, it is based on some physics. To stay warm enough for liquid water, a planet orbiting a dim red dwarf must huddle incredibly close to it. This habitable zone is a tight, cramped space, often closer to the star than Mercury is to our Sun. This close in orbit creates two potentially fatal problems. First, these stars are violent, especially in their youth, the first billion years or so when life would be trying to start. Red dwarfs are unpredictable monsters. They unleash superflares thousands of times more powerful than any solar flare our Sun has ever produced. These flares blast their inner planets with a sterilizing bath of high-energy X-rays and ultraviolet radiation enough to strip mine an atmosphere and scour a planet's surface clean of any complex chemistry. Second, there is the problem of tidal locking. Just as our moon always shows the same face to Earth, a planet this close to its star will become tidally locked. One side of the planet is trapped in a permanent scorching day, while the other side is locked in a permanent frozen night. Kipping and others argue this is a recipe for atmospheric collapse. Any atmosphere the planet has would simply freeze solid on the night side, leaving the day side a barren, airless, irradiated desert. For years, this was a strong theory. Now this camp has observational evidence. Their "I told you so" moment has been coming from the James Webb Space Telescope. As this revolutionary observatory began to study the atmospheres of the most famous red dwarf planets, it has often found nothing. A blank. No thick Earth-like blanket of air. The data suggests these planets are exactly what the solar hegemony camp predicted: bare, lifeless rocks. The radiation from the parent star, they argue, has successfully boiled off their atmospheres, leaving them naked to space. The red dwarf resilience camp. On the other side of this great divide is the resilience camp. These scientists argue that the Kipping view is far too pessimistic and frankly guilty of a profound failure of imagination. They believe life is tough and that we are being Earth-centric. We are assuming that the only way for life to exist is the way it exists on our specific planet. The resilience camp has three main counter-arguments. First, they argue that surface life is not the only option. We are obsessed with the surface because we live on the surface. But on a tidally locked red dwarf planet, the real action might be underground. The constant gravitational tug-of-war from the nearby star could keep the planet's core molten through tidal heating. This internal heat could create a warm, stable liquid water ocean beneath a thick protective shell of ice. Think of Jupiter's moon Europa, but as a full-size planet. Life could thrive in this dark subterranean ocean powered by geothermal vents. It would be completely safe from the flares and radiation on the surface, living in a global oasis that could last for trillions of years. Second, the resilience camp points to new computer models from 2023 that challenge the defenseless planet idea. These models show that even a tidally locked planet could generate a powerful magnetic field. This field would act like a cosmic umbrella, deflecting the star's worst particle storms and helping the planet hold on to its precious air and water. The flares are bad, yes, but a planet with a good magnetic shield could potentially weather the storm. Third, they play the ultimate trump card: time. Red dwarfs are not like our sun, which will die in a few billion years. Red dwarfs live for trillions of years. The intense life-destroying flare activity is largely a problem for the first billion years. After that, the star settles down into a long, stable, quiet adulthood. The resilience camp argues that this provides an almost unimaginable stretch of time for life to emerge, or for a scoured planet to regenerate its atmosphere through volcanism. The first billion years might be hell, but the next 1 trillion years could be paradise. The evidence tilts the scum. For a long time, this was a stalemate between two compelling sets of theories, but in the last couple of years, the first pieces of hard data have arrived, and almost all of it has been a terrible blow to the resilience camp. The new evidence is leaning heavily in Kipping's favour. The most devastating news came from the James Webb Space Telescope's observations of the TRAPPIST-1 system, which were analysed in 2005. This system was the poster child for red dwarf habitability, 7 Earth-sized planets, several in the habitable zone. The telescope stared at one of the inner planets, measuring its temperature as it moved through its orbit. The goal was to check for heat redistribution. If the planet had an atmosphere, that atmosphere would act like a blanket, trapping heat and moving it from the hot day side to the cool night side. The night side would still be somewhat warm, but the James Webb Space Telescope found the exact opposite. The day side was scorching and the night side was freezing. There was no heat being moved around. This is the classic signature of an airless bare rock. More bad news came from the ground. In 2024, the extremely large telescope, a new behemoth observatory in Chile, pointed its powerful eye at our closest neighbour, Proxima Centauri b. This was a direct attempt to sniff its atmosphere for the chemical fingerprints of life. The results were a profound, deafening silence. The telescope found no trace of oxygen, no water vapour and no methane. It found nothing. A final fading hope. Is the case closed? Are red dwarfs sterile? And are we truly alone in our cosmic neighbourhood? There is one last elegant theory that the resilience camp is holding on to. Championed by astronomers like Lisa Kaltenegger, it is known as the cloud feedback theory, and it attempts to solve the tidally locked problem. The theory goes like this. On the permanent day side of the planet, the intense starlight would evaporate massive amounts of water from a surface ocean. This would create a giant, permanent, brilliant white shield of clouds. These clouds would act as a planetary mirror, reflecting a huge portion of the star's light and radiation back into space, protecting the surface and keeping it from being boiled away. This would create a stable eyeball zone. In the permanent twilight ring between the scorching cloud-covered dayside and the frozen night side, there would be a band of perfect temperate conditions where liquid water could exist. The planet would look like a giant eyeball with the dark pupil of the habitable ocean staring out from the white sclera of the reflective clouds. It is a beautiful, compelling idea. It saves red dwarf habitability at the last possible second. But as of right now, it is just a theory. We have absolutely no observational evidence that this cloud feedback mechanism actually happens. It remains the final untested hope for a galaxy teeming with life. We have wrestled with the profound, dizzying question of where we are. We've looked at the flatness of our universe, the razor-thin value of the cosmological constant, and the unsettling realization that our existence seems balanced on the head of a pin. We are adrift in a spatial paradox. But there is a second, equally baffling puzzle. It is not about where we are, but when we are. This is the paradox of time. Let's lay out the facts. We know with remarkable precision that our universe is 13.8 billion years old. We also know that the first stars and galaxies lit up the darkness relatively quickly. Our own solar system formed about 4.6 billion years ago, and life on Earth ignited not long after. From that first spark to us, an unbroken chain of 4 billion years. So here we are in a 13.8 billion-year-old cosmos. The puzzle is this: why did life arise so early? This question might sound strange. After all, 13.8 billion years feels like an eternity. But in the grand total lifespan of the cosmos, it is nothing. It is the cosmic dawn, the very first moments of the morning. The universe in all its potential has trillions upon trillions of years left to live. The heart of this problem lies with the stars. When we look up, we are biased by our own sun, a bright yellow G-type star. We think of it as average, but it is not. The vast overwhelming majority of stars in our galaxy, something like 75% or more, are not like our sun. They are small, dim and cool. They are red dwarfs. These red dwarf stars are the true galactic population, and they have one incredible defining feature: their lifespan. Our sun will live for a total of about 10 billion years. It is a stable but temporary home. A red dwarf, on the other hand, sips its fuel so slowly that it can live for trillions of years. Not billions, trillions. 10 trillion years is a conservative estimate for many of them. Now think about this statistically. If life can arise on planets, and most planets orbit red dwarfs, and those red dwarfs exist for trillions of years, where should we expect to find ourselves? We should, by all statistical probability, be living in the distant, distant future. We should be a civilization that evolved 500 billion years from now, or perhaps 2 trillion years from now, orbiting a dim, ancient red star. The 13.8 billion year mark where we are right now is the tiniest, earliest sliver of the cosmic timeline. For us to appear here orbiting this kind of star is like showing up to a party that lasts for a year, 5 seconds after the doors open. It makes us seem impossibly statistically spectacularly special. This is the red dwarf problem. If the universe has a quadrillion years of habitable real estate available, why are we here now in the first 5 minutes? Why are we the statistical anomaly? This is where the physicist David Kipping offers a breathtaking solution. It is a form of temporal fine-tuning. The solution is so elegant it feels like an epiphany. What if our core assumption is wrong? What if red dwarfs are in fact terrible places for life? We assumed they were great candidates because they are stable and long-lived, but they have a dark side. To stay warm, a planet must orbit a dim red dwarf extremely closely. This close orbit almost certainly results in tidal locking, where one side of the planet permanently faces the star, a scorched endless day, and the other side faces space, a frozen endless night. Life might struggle to exist in the twilight ring between these two extremes. Even worse, young red dwarfs are incredibly violent. They unleash super flares of X-rays and ultraviolet radiation thousands of times more powerful than anything our sun produces. These flares would blast any nearby planet, stripping away its atmosphere, boiling its oceans and sterilizing its surface. Perhaps over trillions of years, life cannot get a foothold in these violent locked systems. So what about the other end of the scale? What about the giant bright blue stars? They are magnificent, but they live fast and die young. They burn through their fuel in mere millions of years, exploding as supernovae, long before complex life, which took us 4 billion years, could ever have a chance to evolve. This leaves a Goldilocks category of stars. Stars that are not too big and not too small. Stars that are stable, not too violent, and live just long enough. Stars, in short, exactly like our sun. These stars, G-type and K-type stars, have lifespans in the range of roughly 5 to 15 billion years. Suddenly, the paradox evaporates. If the only stars that can reliably produce technological observers are sun-like stars, then the cosmic timeline for life is not trillions of years long. The window for intelligent life is defined by the lifespan of these specific stars. This forces intelligent life to appear early in the universe's history. The universe is 13.8 billion years old. The first stable sun-like stars with the right metal content to form planets could only form after the first generation of giants exploded. This means the prime window for life is right now. We are not early, we are precisely on time. The entire habitable era for complex sun-loving life like us might only last from, say, 10 billion years to 20 billion years into the universe's history. We find ourselves at the 13.8 billion year mark because this is the window, it is the only window. This brings us to a deep and perhaps final realization. The universe looks the way it does because we are here to see it. This is the famous anthropic principle. We look out at the cosmos and ask, why is the universe 13.8 billion years old? The answer reflected back at us is because it takes about 13.8 billion years to make you. It takes that long for the first stars to forge heavy elements, for those elements to cluster into new stars and planets, for a planet to cool, for life to spark in its oceans, for evolution to work its slow magic, moving from a single cell to a complex creature that can build a telescope and ask the question. If the universe were only 1 billion years old, we would not be here. The ingredients for us wouldn't even exist. If the universe were 100 trillion years old, we would not be here. Our sun would be a long-dead cinder and the cosmos would have entered its long, cold, dark era. The red dwarfs, we are unsuited for being the only dim lights left. Our perception of reality is filtered by the conditions that allow us to perceive it. We must find ourselves on a temperate, rocky, water-covered planet. We must find ourselves orbiting a stable, midlife, sun-like star. And we must find ourselves in this specific early era of cosmic history. This is not a coincidence. It is a selection effect. We are the observers. The fact of our existence is the most powerful piece of data we have. The puzzles of where we are and when we are, the spatial paradox and the temporal paradox, may have the same answer. The universe is not fine-tuned for life in general. It seems to be fine-tuned for us, because if it were any other way, we would not be here to notice. So after all this, after our long journey through the cosmos, we must ask the biggest question of all: what does any of this mean for us? For humanity? We have looked at the building. Blocks of life, the birth of stars, the formation of planets, and the violent, beautiful dance of the universe. And it all leads back to one simple, terrifying question that has haunted us since the first time we looked up at the stars. Are we alone? The answer, based on everything we are now learning, is a profound and almost certain no. We are not alone, but this answer is more complex and far more interesting than we ever imagined. It's not a simple yes or no. Believing we are the only life in a universe with 2 trillion galaxies is statistically impossible. The true answer is that we are almost certainly not alone, but we are almost certainly special. Think of it this way. We are not members of a vast, crowded galaxy teeming with countless advanced civilizations like something out of a science fiction movie. Instead, we are members of a very exclusive club. The conditions required to get to complex, intelligent, self-aware life are incredibly specific. You need the right star, a stable G-type star like our sun. You need the right planet, a rocky world in the Goldilocks zone, not too hot and not too cold. You need liquid water. You need a stable orbit, perhaps protected by a giant gas planet like our Jupiter, which sweeps the solar system of deadly asteroids. You need plate tectonics to recycle minerals and a magnetic field to shield you from radiation. The list of requirements is long and difficult to meet. While simple life like bacteria might be incredibly common, sprinkled like dust across the galaxy, the leap to complex life, to animals, to consciousness, to us is a bottleneck. It's a high wall that very few, if any, planets manage to climb. How many? We can only guess. But perhaps in our entire Milky Way galaxy there are only a few. Perhaps there are 20 million Earth 2.0s scattered across the entire visible universe. 20 million is a huge number. But in the context of trillions of planets, it is a tiny, precious handful. We are not a miracle, but we are rare. We are part of an elite cosmic club, and this leads to an even more stunning realization. For decades, we have worried that we are late to the party. We've looked at the stars and thought the universe is 13.8 billion years old. Surely other civilizations started billions of years before us. Where are they? Are they watching us? Are they so advanced they have become gods? But what if this is entirely the wrong way to look at it? What if we are not late? What if we are in fact right on time? This idea is what we might call cosmic synchronization. The universe itself had to cook for billions of years just to make life possible. The first generation of stars had to be born, live and die in massive explosions just to create the heavy elements, the carbon, the oxygen, the iron, that our bodies and our world are made of. This process took time. Billions of years passed before the universe was rich enough in these materials to even form planets like Earth. Then those planets had to cool and stabilize. It's possible that the window for complex life to arise in the universe has only just opened. The conditions across the cosmos have only recently, in the last few billion years, become truly ripe for intelligence to bloom. If this is true, it means we are not late. It means that all across the universe, on all 20 million of those other Earths, civilizations might be waking up at the same time as us. We are not coming into a mature ancient galaxy. We are the first generation. We are the pioneers. We are all waking up together in the vast, quiet cosmic morning. This idea is thrilling, but it is also deeply sobering. It places an incredible weight, a profound responsibility on our shoulders. If we are the pioneers, there is no one to help us. There is no one to ask for directions. We are the ones drawing the map for the first time. And if we as pioneers fail, the consequences are staggering. If we destroy ourselves, whether through nuclear war or by failing to manage our climate or through some new technology we invent but cannot control, we are not just ending one civilization. We might be slamming the door on complex life in this corner of the galaxy for billions of years. If we extinguish the light of consciousness on this planet, that light may not get a second chance. The universe may have to wait for another billion years or 3 billion years for another lucky planet to run the gauntlet and produce a species that can look up and wonder. This makes our mission clear. It is no longer just a good idea to protect our planet. It is not just a nice thought to preserve the other species we share this world with. It becomes a cosmic imperative. It is our sacred duty. We have a responsibility not just to ourselves or our children, but to the universe itself. The universe has worked for over 13 billion years to produce us. We are the one chance, the one experiment that finally succeeded in this solar system. We are the universe's way of becoming aware of itself. To fail now to let this incredible gift of awareness flicker out due to our own foolishness would be the ultimate tragedy. This changes everything. It changes our entire philosophy. For centuries, we have lived under the Copernican principle. Copernicus taught us that we are not the center of the universe. This was a good lesson in humility. It taught us that the Earth is not special, the Sun is not special, and we are just an average planet orbiting an average star in an average galaxy. It taught us that we are nothing but a speck of dust. But this new understanding suggests a shift. It moves us from the Copernican principle, the idea that we are average, to a new idea, one we might call the optimized template. We are not average. We are not a random fluke, this solar system, this planet us. We are what happens when the conditions are perfect. We are the result of an optimized process. We are the template. We are the pattern that the laws of physics and chemistry work toward when all the conditions are met. We are not a cosmic accident. We are a cosmic destiny. We are not a fluke. We are the blueprint. This doesn't mean we are the center of the universe in a physical sense, but it does mean we are profoundly meaningful. We are not just a random collection of atoms. We are the universe's most complex and beautiful creation finally awake. And with that awakening comes the ultimate responsibility to survive, to learn, to explore, and to carry that spark of consciousness forward into the future, whatever it may hold. For so long, our quest for life in the cosmos was guided by a simple, powerful idea: go where the real estate is. We pointed our telescopes at the most common stars in the galaxy, the M-type red dwarfs. They are plentiful, numbering in the trillions, and we found that planets around them are just as common. It seemed like a numbers game, a cosmic lottery where buying more tickets would surely give us a winner. But as we have learned, not all homes are created equal. These crimson suns are often violent and unstable, and their planets are locked in a harsh, permanent embrace. And so we stand at a turning point. We are shifting our focus. We are coming home. The future of the search for life is not about casting the widest possible net. It is about a precise, focused, and deeply personal hunt. We are changing the mission. This new chapter will be written by incredible new instruments tools powerful enough to do what was once science fiction. The upcoming Habitable Worlds Observatory, or HWO, is the new flagship of this quest. Its mission is not to scan the galaxy broadly, but to stare deeply at a handful of the most promising targets. It will turn its powerful eye towards stars that remind us of our own, the stable, nurturing G-type and K-type stars. We already have names on the list. Worlds orbiting stars like 82 Eridani or Tau Ceti stars that are cosmic cousins to our own sun. The goal of the HWO is not just to find more planets, its goal is to understand them. This observatory will have the power to analyze the light from these distant worlds to read the chemical fingerprints in their atmospheres. It will hunt for the very things that signal life on Earth, the signature of oxygen from plants, the whisper of methane from living organisms, the unmistakable presence of water vapor. We are no longer just looking for a stage, we are looking for the actors. At the same time, the search for intelligent life is also refocusing. The SETI Institute, through the revolutionary new Square Kilometre Array or SKA, is embarking on its most targeted search ever. The SKA is a vast network of telescopes, a continental-sized ear pointed at the heavens. It won't be listening at random. Its new strategy is to aim directly at the 200 nebda nearest stars that are just like our Sun. This is a profound shift. We are moving from a strategy of shouting into a crowded stadium, hoping someone hears, to a strategy of leaning in to listen to a quiet conversation in our own neighborhood. We are assuming that if another technological civilization is out there, it likely emerged in conditions similar to our own. This pivot carries with it a deep philosophical weight. The meaning of our search changes completely based on what we find or what we do not. If we look at these golden lightened stars, these perfect candidates, and we find nothing, if we scan their atmospheres and hear only silence, the conclusion is staggering. It would tell us that we are not just rare, but perhaps miraculously, terrifyingly rare. It would mean that the jump from chemistry to biology, or from biology to complex, intelligent life, is a barrier that is almost never crossed. It would mean that this blue marble, this Earth, is an island of impossible complexity in an ocean of sterile beauty. The responsibility of that discovery would be immense. We would be the sole guardians of consciousness, the only voice of the universe for light years in every direction. But what if we do find it? What if the HWO detects oxygen on a world orbiting Tau Ceti? What if the SKA picks up an undeniable structured signal from a nearby sun-like star? If we find it, we confirm the pattern. We would learn that Earth is not a miracle but a blueprint. It would mean that life is not a one-time accident but a fundamental and persistent property of the cosmos. It would mean that the universe is built for life and that the stars are teeming with potential. We would instantly know that we are not alone. We would be a new member, the youngest member of a vast cosmic family. This is the real story of our search. We have spent years chasing the most common light in the galaxy, the faint crimson glow of the red dwarfs. But we are realizing that the true search, the one that echoes our own story, is the hunt for the golden light. We are looking for the rare, precious, steady glow of stars just like our sun. We are not just looking for any life, we are looking for a reflection of ourselves. In the end, our final understanding of our place in the universe comes down to a single word: special. For centuries we have argued about whether Earth is special, and now we see the answer. Earth is not special in the sense that it is a unique one-of-a-kind miracle that can never be repeated. Instead, Earth is special in the sense that it is a perfect representative of a pattern. We are the proof of concept. We are the evidence that under the right sun with the right ingredients, the universe can wake up and look back at itself. And that is the ultimate hope. It is the belief now driving our greatest scientific missions that somewhere out there right now orbiting another gentle yellow sun is another world. A world that has gone through its own long journey from dust to life. And on that world, under a familiar golden sky, another mind is looking up asking the very same question that we are. Thank you for joining us on this journey through the cosmos. If these ideas sparked your curiosity, please be sure to subscribe and like this video. We want to know what you think. Drop your answer in the comments below to our one great question. Are we alone? Or are we just one part of a vast silent cosmic network all waiting patiently to connect?